Now this might look like a standard SFP optical module. On one side, we got our fiber optic interface. On the other side, we fit in the SFP cage. But this guy is actually really special. You see, this is a whole-ass computer in the SFP module. It's got 2 ARM v8 processing cores, and it has a gigabit MAC on both the SFP side and the fiber optic side. It can intercept, read all of the packets across the wire, can do bridging, routing, basically anything you could do on a server with 2 gigabit Ethernet ports, except it's stuck here inside the SFP. So if this sounds like something that's really cool to you, then come along on this adventure. So before I get too far ahead of myself, what exactly is an SFP anyway? What is that slot that this little tiny server is going into? Well, it's kind of in the name of the abbreviation. It's a small form factor pluggable transceiver slot, SFP. So you guys remember our friend, the OSI model, right? You've probably heard it before somewhere. Even ignoring the fact that the whole OSI protocol suite is entirely obsolete, it's still kind of useful for this discussion, because essentially this small form factor pluggable transceiver is the interface between layer 1 and layer 2. So layer 2, the link layer, is responsible for things like framing, serializing data buffers like bytes into ones and zeros on the wire. And so the MAC, the media access control, does that in Ethernet. Then it sends those very theoretical ones and zeros to very real analog signals using the PHY, layer 1. So normally an SFP transceiver is taking in sort of arbitrary, like theoretical ones and zeros, like very high quality ones and zeros, like definitely zeros, definitely ones, and converting it into some sort of analog encoding with optics or with line drivers. So that's voltages on the wire, photons of light, the real actual representation of those ones and zeros. So we need this choice of physical layer because there are very different options we have for sending a digital signal long distances, depending on how long the distance is, if we want to use glass fiber or copper. For example, this transceiver built in to the Smart SFP, this is a 1310 nanometer for single mode fiber. That's what I'm using it with. I got a matching 1310 nanometer plain transceiver on the other side of the link. Maybe I need an 850 nanometer multimode fiber transceiver. Maybe I want to use gigabit Ethernet, which only runs over 4 pairs, use a trellis code, much more complicated analog encoding. Or maybe I'm using like gigabit T1, which is the automotive standard that runs over a single pair. So all of those are different physical layers, different analog line drivers that are converting the ones and zeros from the MAC into actual voltages on the wire. But of course, if we're only going a really short distance, maybe the digital ones and zeros coming out of the MAC can actually survive for a couple of feet or something. That's what direct attached copper cables are. They use what's called a twin ax. Just send the ones and zeros straight out of the MAC, straight into another MAC on the other side of the link. So what if we were to just take like a CPU that has an Ethernet MAC and put it in the transceiver slot connected straight up to the other MAC? That's essentially what this does. So this guy has a CPU inside that has 2 Ethernet MACs. So that's doing the layer 2 stuff. One of them is connected to the SFP side, so it can speak to the other side, whatever the SFP is plugged into. And the other side is connected to the transceiver. And that means that this Linux system in this box has 2 gigabit Ethernet interfaces, one of which is connected to our SFP carrier, and the other which is connected to our lasers. So it's pretty simple. There's a whole lot we can do with this arrangement, so I got some tricks planned for this video. So let's hop into those. So for my first trick, I'm just going to do some basic packet inspection with Wireshark. So I got a virtual machine running on here hooked up to this. This is just a 1 gig fiber. It's hooked up to the Smart SFP back on my switch. I needed to be on my switch there so it gets cooling from the fans. So as far as everyone on the network can see, this is just plugged in to a switch with an optical cable. It's on the LAN, it's not on a different network or anything. Packets flow normally, it has an IP address, etc. The VM does. And there's nothing in the middle. But of course, the Smart SFP is sitting there. It has a link local IPv6 address, so it doesn't even appear on the network either. If you looked at your DHCP leases or even your IPv6 global clients, you wouldn't see it there. But it is advertising itself over MDNS, so I can find it, and I can log into it over Wireshark and capture packets going to and from this VM. So over here in Wireshark, I'm going to use SSH dump. I'm going to use smart SFP.local port 22, and I'm going to log in as, I'm going to capture an interface BR0, and let's go. It'll take a few seconds to get started, and I should start seeing packets coming in soon. There they go. So now on my VM here, I can go to appleart.net, load my web page, see if I can find this in the packet log. So I was expecting something TLS, but it's not TLS, it's Quick. Here we go, appleart.net. So we connected over Quick, so I can't lock any of the traffic, but you can see I got a pretty thorough collection of what happened on this wire. So simple as that. I just plug this SFP module in anywhere on my network. I connect to it over MDNS, so it's the same broadcast domain. But I could do fancier stuff to connect to remotely, so let's try some fancier things, I guess. So for my second trick, I wanted to do some packet analysis. So capturing with Wireshark is all well and good, but many people like to do like security analysis or that kind of stuff relatively deep in their network. So I have an OpenSense firewall. I've made plenty of videos on that. One of the tools I've used for many years now is NTOP-NG. I haven't made a video on that, but I probably should. And so NTOP-NG supports a mode where you run it in different places on your network and aggregate all the data. Similarly, you can do it with NetFlow or more dedicated like security software that can analyze all the flows through deeper levels of your network. Now for me, I only have the one closet here. I don't really need that. But if you have a more expansive network, you might get more security data by monitoring more points in your network than just your core firewall. Now I'm running NTOP-NG, the whole thing, directly on the SFP stick. So the SFP stick has enough RAM to run it. The UI is a little bit slow, but I'm running it on the stick because the community version that's open source doesn't support remote probes, which kind of sucks. And I didn't want to deal with trying to compile the open source version without licensing. So I'm running it on the stick itself. I come over here to the web UI. So here's NTOP-NG. We can see got a hell of a lot of traffic going here. So I click on this. No, go there. Who is that? Google. Yep, probably because someone's watching YouTube. And I happen to know they're watching YouTube, so we're sending what we got here. So this particular flow is not sending a huge amount of data. We haven't even got to a megabyte yet, but we've got a lot of flows going to all kinds of different CDN servers. And you can see it's not the fastest, but it's totally working here. So the data loads. You can see not a whole lot's going on, but we can see what's going on here. You know, we're on the Smart SFP2, so we can see NTOP-NG is running. I just had to install it with the normal methods. So this might be useful to you as like a deployable probe in your network. If you think something might be suspicious going on somewhere, you can deploy this probe to the nearest switch. It just sits in the SFP slot, can monitor traffic, report back on things it finds. If you find the right open source package, it's not that hard to run it on the SFP. It's just running standard Debian bookworm. You can use apt install, everything you need. It doesn't have the most space if you have any tools that are large, but you've got about a gigabyte to work with in both RAM and flash space, so certainly usable for stuff like NTOP or other security monitors. So I also did a bit of performance testing in the background off camera. So both with basic bridging, that's the setup I had earlier, with NTOP-NG, also with basic routing, that's from doing IPv4 or IPv6 forwarding, and IPv4 NAT, so like a sort of home firewall kind of setup. In all of those cases except NTOP-NG, I was able to hit line rate iPerf3. Now, iPerf3 is kind of a best case. It's running the largest packet size possible, 1500 bytes. It's only sending one stream, so we don't have a lot of NAT sessions to worry about. So in the best case, this could handle line rate. However, it falls off pretty fast with smaller packets. So even during the TCP ramp up, as it's adding bigger and bigger packets to try to find the maximum size, it would not be able to handle line rate there. Running NTOP kicked me down to about 600 megabits. Running IPv4 NAT surprisingly didn't add any throughput overhead. So with 1500 byte packets, it was able to handle that. But again, with smaller packets, it was not able to handle line rate. It's limited by packets per second. And that makes sense because all of these packets are being processed by the dual-core ARM v8 CPU, which totally makes sense, but just be aware that if you're running really intense applications on this thing, there will definitely be a performance hit to your networking performance. So next trick I got is an IPv4 only island. I got this Ubuntu virtual machine here, and we're pretending like it doesn't support IPv6. Maybe it's some old ass system that you still got to keep running in the modern world. Maybe it's some embedded device, something like that. Anyway, I developed Taiga, which is an open source IPv4, IPv6 translator. It's a stateless IP and ICMP translation. You can use it to build out NAT64. Link up here to my GitHub on that, by the way. So I thought that would be a neat application of this. So the Smart SFP is again in my rack. It's set up as a router this time. So it has a proper IPv6 address on the IPv6 only network. It actually has 8 of them. One of them is for the translator, one of them is for the Smart SFP, and 6 of them get passed on to v4 only devices here. So on the fiber, it's doing DHCP v4, handing out DHCP v4 addresses to clients, such as this Ubuntu VM here. The Ubuntu VM can do IPv4 DNS, IPv4 traffic, and then that gets translated back to IPv6, sort of like 464 XLAT. So, neat little use case. I can build out an IPv4 only island within my IPv6 only network. So here in Ubuntu we see we have an IPv4 address, we have a route, we have DNS. We don't have v6 though, so we got nothing. We have it turned on, but we're not getting it. But I can come over here to applr.net, I can refresh all over 464 XLAT. Now I wasn't able to do SciProof testing on this because SciProof only supports v4 end-to-end, so I would have had to set up a second translator on the SciProof server, and I didn't want to do that. But iProof testing, I get about 350 megabits through this on the Smart SFP. Taiga is also only single-threaded, so Taiga performance is never that great to begin with. So even on a good system, you only get about a gigabit of Taiga performance with the current version of Taiga. We're working on that, by the way. So this is not awful. I'd be pretty happy with this. If you have legacy v4 only devices, they're probably not your fastest devices anyway, so good job. So if we can do routing, why can't we do VPNs too? So we got 2 interfaces. In this case, I've got the SFP interface in the Smart SFP set up to my v6 only network. It's making a WireGuard connection out of my network to VPN server in Finland. So from the point of view of this network, it's just got one address. That's the Smart SFP itself. It's making only outgoing connections, so no ports are being opened on any of my firewalls. And now I've got a private network to have global v4 and v6 for my virtual machine here. So over here on the VM, you can see I ran test IPv6, and I appear like I'm coming out of Finland. I can do speed test 2. It's probably not going to be great. I'm not expecting much, but it's probably usable. What is using all my CPU here? Is it WireGuard Go? It looks like it's WireGuard Go. So as you may have noticed, I'm using WireGuard Go there, which is the user space implementation. WireGuard Go is not as fast as kernel WireGuard. It's also not threaded the same way, so it relies on the TUN-TAP adapter, which is multi-queue, but is always going to do consistent hashing, so my one single TCP session is always going to the same core. It's only a dual-core CPU, so it's not that big of a deal. But the kernel on this Smart SFP doesn't have a lot compiled in. So WireGuard is not compiled in. A lot of IP tables, NetFilter modules are not compiled in. There's no multiple table support for multiple routing tables. There's no VRF support. There is network namespace support, so I was able to utilize that to get this setup working correctly. But it meant I couldn't use any of the example scripts on the internet that use multiple tables. But it's working fine. I have all the configs on my blog, by the way, for all of these things I've tested up to this point in the video, and all of my detailed test results if you're curious. But so I got this working. I'm not getting great bandwidth, mostly because I'm limited by the crypto performance of WireGuard. If I was doing something AES-based, I might do better. I'm actually not sure if this chip has hardware AES either, but I guess I have to test that too. Okay, it looks like we do have ARM v8 crypto, and AES is pretty fast. So that's the tricks I got for you in this video. This little guy here, the Smart SFP by Plumspace. I thought this was a really, really cool device. So it's not that powerful computationally. It's a dual-core ARM Cortex A53. I think it's running at 1.0 gigahertz. 1 gig of RAM. It has 4 gigs of eMMC, but it's partitioned in a way where you can't exactly use all of it. So there's a 1 gig root partition that's normally read-only, but you can mount it read-write. Because they've done this read-only root partition, they have a separate home partition and a separate var partition that are read-write. And that means that we have not a whole lot of space on any of those partitions. And then we have one partition left over for the upload process, and I think there's a redundant boot partition or something like that. There were quite a few partitions on the partition table. I didn't take a deep look at it. I found because of the partition layout that it was very hard to install software. So I would often have to download files and put them in var. I couldn't download them at home because home didn't have enough space. If I downloaded them on root, then I wouldn't have space to extract the files, so I could put the tar.gz in var and then extract it into root or stuff like that, or do like a pipe between curl into gzip into file system so that it wouldn't consume too much space with the targc. Because of that, I did have a couple issues. So things that I tried that I wasn't able to get to work. So first off, I tried nprobe. That's the remote probe for NTOP NG. And I had licensing issues on that one, which is entirely NTOP's fault, not the Smart SFP. So in that case, I ran the whole NTOP NG on the Smart SFP itself. And that worked well, but it took all of the space I had to store the little bit of log files I had, and the program itself was quite big. So I anticipate that if I would have continued like this, without an external log server to store the time series data, I would have filled up this whole eMMC real quick. Which might not be a problem for you if you're using this for like drop-in testing, that kind of thing, or if you have access to a remote server where this is being your probe, and you have a central data center somewhere that's storing all the data from all the probes, that could be a great option for you. So next problem I ran into was running WireGuard. So most people just run like WG quick up WG0, that reads the config file, does everything you need. I couldn't do that for a couple of reasons. First off, I don't have the WireGuard kernel module. So the operating system on this thing is based on Debian, but so you can run apt-get, you can install app packages from Debian's repositories, and anyone who has a third-party repository, like for the Raspberry Pi, AR64, for Debian, ARM in general, that'll probably install on this, probably without issues. The problem is the kernel has been stripped down to make it smaller, and that would make sense in a lot of cases, but given this as a network device, I think it would have made sense to include WireGuard in the kernel. Also, a number of NetFilter modules were pulled out, which again would probably make sense, but NetFilter, you can't really compile stuff as a module and modprobe it. It has to be linked in at compile time to the kernel. So I wasn't able to compile EBtables. So EBtables is used to do layer 2 bridge filtering, and EBtables isn't in the kernel. So I couldn't do EBtables NAT, I couldn't do EBtables BRoute. I wanted to have a case where I was doing BRouting rules for a transparent inspection bridge, like Squid proxy in transparent mode, but unfortunately I couldn't, so that was out. I did actually try to compile the modules myself, but I didn't have enough space on the device for GCC and the Linux headers, which was kind of unfortunate. And I didn't want to take the time to set up a 64-bit ARM environment, so you could probably make it work. It would probably be easiest to recompile the kernel. I think I mentioned, I'm pretty sure the kernel came from Marvell, so it doesn't exactly say, but I'm pretty sure this is running a chipset made by Marvell, specifically the Marvell Armada 3700. I found some references in like dmessage to that, so that's what I'm pretty sure this is running. That has matching specs to this, so that would make sense. Not a guarantee though, but that's where I believe the kernel came from. I don't have the kernel sources with me. I didn't ask for them, but I could if you want me to, I guess. What else did I try? Oh, also for WireGuard Quick, it's not compiled for multiple table support. So like in Linux, there's like 3 different ways to do VRFs. So you can do them with network namespaces, you can do them with multiple tables, and you can do them with VRFs. Now, I don't know why they have VRF interfaces and also multiple tables and also namespaces, because it would seem like you would just need namespaces to do VRFs properly. But no, we have VRFs and namespaces, and they're separate. So anyway, normally in WireGuard, what you do is you set the default route to the WireGuard interface, but then WireGuard itself still has to send packets on the normal network, so you use a separate table for that. And WG Quick couldn't do that because there's no table support in the kernel. There is namespace support though, so I did it with network namespaces, and that worked fine. So see my blog for the commands I used. I tried to run MITM proxy. It's similar to Squid, but designed like for developers. So it's much more focused on having a good UI than being performant. And again, that needed EBtables to run in transparent mode, which I didn't have access to. I couldn't compile it as a module. The next option is to run VPP. So this supports DPTK. It has a lot of the libraries needed for DPTK already on it. VPP is a common routing platform that runs with DPTK. I did not find versions of it compiled for ARM64, and I didn't want to take the time to compile it because compiling stuff on this thing is real slow. So I didn't, but that's where I got with my testing. Now again, we have to set expectations straight for this thing. This thing is plugging into an SFP slot. It can only use a couple watts of power, so we're limited in how much electrical power we can pull from the slot. We also still have to drive our laser optics, because we still have an optical transceiver. So the power available to the CPU and the RAM and the eMMC is like 3 watts. So that's the best they can do. With that, they've put in this dual-core ARM Cortex A53. It's able to get a decent amount of stuff done. Now, all the examples I had, I was using it like as a network pass-through, as a router, as a switch, something like that. You don't actually have to connect both sides of it if you don't want to. So you could just plug it into a switch on the SFP side and just use the SFP interface. Then you could run any sort of local software you need, if you need like a local radius server or like a local cache or something on a local network where you don't want to run like a whole mini PC. This could sit in your network switch, be a nice compact thing. It also could use just the optical interface, I guess, if you had some sort of carrier. Like I have, where do I have that thing? This is my TP-Link MC220. I can pop the SFP module in here just to power it if I want. So just not use the RJ45 and just use the fiber if I want to connect over fiber or something. They kind of advertise this as being able to be used as like a remote probe. They call it like an SLA probe. So you can put it somewhere in your network, do continuous stream of measurements across between this and some server in the cloud, and be able to tell what the connection status is, if the connection's reliable, what the latencies are, that kind of thing. Just having a device that you can install your own software on can be very useful for that. So anyway, I'd love to hear your guys' applications for this one in the comments. They also have a couple of other options. They have one with a USB, one with an RJ45 Ethernet, one with an RJ45 serial, and then I think this is the last one with the fiber optic. So if you have any really good use cases for this, I'd love to hear it. I'll probably pass some of the best ones onto Plumspace and ask if they want to do another video with me. We'll see how that goes. They also didn't pay for this video, by the way. They just sent me this one SFP so I could show it off. I love showing off weird things like this, especially SFP modules. This is going to go in my collection that I've got here of SFP modules. In addition to the Mocha ones I did a few weeks ago, I've done a smart, they call it the Smart SFP. It's like an RJ45 console SFP module. That one's in here. I've got normal SFPs too, of course. SFP fiber ONTs. I've got those from my GPON video. I got this now, which is a whole ass Linux system on an SFP. I don't know how we're going to top this, but we're going to have to try to top this. So if you know any weird SFPs, I would love comments down below for that. If you have any weird applications for this Smart SFP, again, comment down below. If you have any leads on the GPS module made by Nokia that's in an SFP form factor that I can actually buy that's not thousands of dollars, I would love that one too. I've been looking for that one. What else do I got? If you want to chat with me more, I got a Discord server, link down below for that. If you want to give me a tip, you can find my Ko-fi. I greatly appreciate any of those. I'm thinking of how I could like modernize the Ko-fi. It's kind of like Patreon, but it's only a one-time thing. I've been debating on like making the recent commenters or recent contributors like scroll on a screen or something. So if that would be beneficial to you, I guess comment whatever you think about that. Engagement always helps. I have a Mastodon, link down below for that as well. And I guess I'll see you guys on the next adventure.